All right, everybody, our next speaker is in charge of after lunch is Brent East, who's the account manager for Thornwood Corporation. So Brent has 18 years experience with the company in a variety of positions. So his current focus is customer needs and assisting them with additive manufacturing and the CNC machining center solutions. So let's welcome Brent East.
So I'm going to talk a little bit about a little bit different subject than everybody else has here. I'm going to go to the large-scale additive manufacturing side of things and a little bit in how that varies from traditional filament-based printing systems. So traditional FDM systems, like I said, are using either a powdered metal or a small filament, and basically pass over the part, creating a net-shaped finished prototype or finished part when completed. Large-scale additive systems work a little bit differently. So we're putting down a much larger bead at a lot different rate, and that's going to require subtractive machining done typically on the same machine once completed. So it's not going to be a finished product coming right off. But you've got the basis there for that finished part. So the main focus of the large-scale systems is looking at the printing of large tools, molds, masters, trimming fixtures, layup fixtures, those types of things. So traditionally, those tools have been made using glued up oversized blanks and then machined away to a finished net shape. Oftentimes you're removing more material than what remains at the end of the day, and most of the time that material is waste product that has to be discarded. With additive manufacturing on the large scale, we can go into markets such as the aerospace, automotive, marine, foundries, and many more, and we can develop tools that can be autoclave ready, directly off the machine, skipping several steps through the production process, compression molds, and again, fixtures, you name it. There's a lot of various materials. There's a few material suppliers who their main focus is just on materials for this large-scale market, making sure that materials such as the ABS, PPS, polycarbonate, Ultim, the nylon 6s, are all there and ready to be used now, but they're developing others as well. And almost all these materials are going to be combined with either carbon fiber fill or glass fill for structural and CTE properties. The traditional methods are going to go back using, ring shape aluminums. Some of those can get rather expensive. There's a lot of time and labor involved in gluing up those initial stock models to machine. Just for instance, I had a customer who was basically, it's about a 4 foot tall, 3 foot cube type part, complex shape. They were going to make this traditional tool out of Ren board. And looking at the overall time cycle of everything, it was going to take 2 of their individuals who were highly skilled, a total of about 16 hours to glue up the initial blank to make this part out of. And looking at the 3D additive side of it, we could grow this part in about 6 hours. So huge amounts of savings there in labor. As you see here, the statistics showing a minimum of probably 50% savings on that. So as I was saying before, depending on the materials that you use and the end process the part needs to be used for, it's possible to skip several steps going straight from the CAD data to the final product tool mold, skipping, creating an initial master patterning, pulling a part off of that, and all the steps in between. That's where most of your savings is going to come from. I've seen numbers all the way up to 70% from some of the guys who've been looking at the system. So in looking at traditional filament base, the net shape versus near net, as we're doing. The net shape guys are basically, with a smaller bead, they're able to get a much smoother than what we are, part coming right out of it. So a lot of times, some minor sanding, that part's ready to go. With ours, you're going to get more scalloping, a larger scalloped edge that's going to require that final machining, trimming to size. This also lends itself, though, to being able to get closer tolerances to hold tighter parts without different coatings and things like that. So also, versus the traditional glue-up methods, you're removing much less material going to that final net shape once done. You may be removing only a 1/4 inch versus inches of material in some places. So basically, once the item is done printing, if you have the subtractive gantry on the same machine, you're able to either machine the part where it is located, or if you have a large enough printer, move it to the opposite end and begin machining while the next part is being grown. You can also, we're working right now with a university who is working on a thermal predictive software. So that can be used on both the additive and the subtractive side to know where your various CTEs are going to be based off of those carbon fiber filaments that are located inside of it, and how to predict that to get the proper size part when grown, and also the proper size part when machined, so when going to the autoclave, you know what kind of CTE properties you're getting out of it. So to kind of give you an overview of what those differences are, the traditional filament size is going to be about 70 thousandths. On large scale side, you're going to run from about 3/8 to a 1/2 inch diameter bead. Now when you start going that large, you need a way to adhere that bead to the previous layer, instead of having a stacked up snowman where you get a small cross section that's actually touching. The best method for that is using a compression wheel. So once that wheel applies pressure to the bead that's being laid down, it's going to compress that out to about 0.83 inches wide from that 1/2 inch bead and about 0.2 inches thick. That's also going to help ensure that there are no air bubbles between the two layers, giving you good layer-to-layer adhesion and virtually zero porosity throughout that process. Another area that's quite a bit different in the large scale versus the desktop type printers is the slicing software and the software used to create the file. Traditionally, STL files are used. If any of you have had experience with those, you know the difficulties in running STL files and the results you get from those. What we have gone to is working from the actual CAD model. We actually prefer whatever native format that CAD file is coming in. We can also run with step files or IGES or Parasolid, whatever it might be. But this gives you the ability to work with that part directly as it was initially created, add whatever internal structure or bracing there might be, add the additional stock for the printing process, and go straight to machining all from the same file. Never jumping formats from your solid model data to an STL back to your solid model for trimming. Ends up with a much nicer part once completed. There's also the ability to print multiple pieces. So why may you want to do that? Well, on ABS, for example, you've got about 1.5 minutes of a minimal layer time that you can put down. So if you're doing a rather small part, you either have to go to a park area of the machine and purge until that time is up when you can start printing again, or if you have a large bed, you can print multiple pieces at one time. So this gives you the ability to grow various parts all at the same time. The current demo machine we have at our lab is 10 foot wide by 20 foot long, for example. So we've got a large area there that we can print multiple parts without affecting that bead time. You can also control the bead width and thickness on the fly. This comes in handy if you're doing a solid print You know, you're not doing a hollow shell or internal bracing. If you're printing a solid model and basically you start stacking the same width bead on top of each other and pressing it down with that compression wheel, by the time you get to the end of your run, your part's going to be quite a bit larger than what you initially anticipated. By being able to vary that bead along the way, you can change that width as you go, and you end up with the right size stock model whenever you're finished. You can also print the boundaries, shell molds, do any infill structure that you want. We've got customers who wanted cooling channels printed into their mold. They were in the marine industry, and basically they needed to be able to cool the corners during their layup process because the finished layup part got so hot. So they were going to run cooling channels internally and be able to cool the mold directly from there. So that was all printed right inside the structure. There's also what we call corner pullback. If you can imagine, as you're laying down the bead, as you come into a corner, that bead is going to want to be stretched or pulled in some fashion by that wheel. So we've actually got simulation and actual software that will calculate that out, extend past that corner, and allow the wheel to pull it back into position. There's also what we call concurrent printing. This allows you to print various models within the same model. As you see the part on the screen here, this is made up of basically 4 different components all printed at the same time to create the same piece. So there's a solid front section followed by a reinforced hollow core behind that, and the same printed on top of those two, and a solid body printed on top of that yet. So this gives you the ability to create very, very complex parts that couldn't necessarily be designed as a single piece. So you can tell the software, for instance, the green part of the model, that is a separate part of the file. It doesn't really know that these are all going to be merged together at the end. It just knows that it starts printing 4 inches higher or whatever that bottom layer is. So again, very complex shapes all printed into one. There's also other accessories for the large scale that you don't have to necessarily worry about on the filament-based machines. Dryers, the material being a polymer. We talked about moisture and wanting to absorb that earlier. Well, you need to remove that prior to printing, so there's large dryer systems that have to be put in place. Basically, you place your Gaylord of material in below the dryer, it loads up the material, goes through the drying process, and then moves that up to the extruder. That's all automatic and all taken care of. So just a little bit easier to operate. If you don't remove all the moisture content from it, you will notice a lot more voids and porosity in your part as you print. So with additive manufacturing, you get a faster turnaround on your parts. There can be a lot more customization to the parts, such as the water channels built in. There's less labor. There's a lot of different, as I pointed out earlier, there's a lot of different material testing going on now to accommodate a wide range of markets that we may want to get into. There's a lot of continued software updates going on. Basically, a lot of ours right now is coming from the end user. As we're doing demonstrations for customers, they're requesting things that we may have not thought of already, things that we need to incorporate into the software to make things easier, to make things more streamlined. So a lot of what we're doing right now is being driven by customer need. We look at it as there's always probably better methods to produce final parts when it comes down to it. We're looking again at this more for the tooling and molds area on the large scale versus finished parts going into production. And then if anybody has any questions on anything, I'll be glad to field those. With the, he was asking what the material throughput was. Right now, the demonstration machine we have has a 40 millimeter extruder on it. We're running just under 200 pounds an hour capacity with that. We also have larger cores as well. where we can run up to about 500 pounds an hour maximum.
What's your max temp of your
With the extruder itself, we're running high temp. I believe we're in the 600C range, where we can run, all the PPS, PPSU, any of those materials without any problems at all. We're running basically a dual system controls on the machine. We've got one control that's set up for the extruder side of everything, so it's handling through a Siemens unit all of the temperature controls, all the thermals throughout the run. We're getting most of our heat in our system, in our extruder, from the barrel heaters themselves. So if you look at traditional extruders, basically they're set up to run a certain pound per hour nonstop. They just set up and run all day long. With an additive extruder, you're constantly stopping, starting. You're coming to a corner. You're always changing. So if you're getting all of your heat from that screw, you're not getting a consistent melt all the time, and you're not getting a consistent throughput. So we run several barrel heater zones on there, and that's what we're getting most of our heat from. That way we're not affected by those changes in speeds.
So you don't see degradation of polymer at higher temperatures?
Well, it's all controlled. It's all going to be based off of what polymer you're running as to what temperature we're running.
Specifically in the thermoplastic?
No, we have not seen issues with that.
How's your surface porosity? I mean, is there much after machining?
Very little, if any. We've actually taken parts right off the machining process and been able to hold vacuum without any issues at all. No coatings, no additional things.
No coatings?
No coatings. We still have people who are wanting to use, coatings for various processes, whether it be release agents or whatever it might be. But as far as being able to hold a vacuum right onto the mold itself, we've been successful at doing that.
Are there any specific design considerations that need to be taken into account for this kind of process?
Definitely.
Thinking about support material like that. So.
Yeah, and it all depends on the material itself that you're planning on printing with, as far as how forgiving it is. We did some testing with some PPS that we did a certain type of interior bracing and everything that actually caused enough stress on the material itself that it cracked across the beads themselves, not in between. The adhesion between layers was perfect, but it stressed itself enough to do that. And most of that was just in the design process. It was also a single bead wide, so the temperature, the cool rate on it was a little bit more rapid than we anticipated, which caused some of that. So we printed the exact same model again without the cross bracing and as a dual bead outside and had zero cracking at all. So there's definitely a consideration in material and design. The ABS is a lot more forgiving. You can put a lot more cross bracing structure and everything inside of there, and you don't see the same issues that you do with PPS. The bead, our standard bead is a 1/2 inch diameter coming out. We're compressing that down to 0.83 wide and 0.2 thick. We're actually working on going up to 1 inch wide compression here within the next couple weeks. We got a project that looks like it's going to lend itself well to that and should greatly reduce the overall time that it's going to take to print this particular mold project.
And cost, again, you said we're about 70% of?
50 to 70%, yeah, of traditional methods of doing that. We'll have some really hard data on that within the next couple of weeks here. Okay. We just delivered a tool to a customer that had already created the same tool using traditional methods. So he's going to do a direct comparison in cost, time, and in results in the autoclave and everything. So we'll have that data available soon.
Cool. That'll be on your blog?
I'm sure it will be everywhere.
Can you comment on the slicing software and Mastercam? Just give a little
Such as?
Such as, is it pulled from the marketplace now, homegrown, and just how we work within Mastercam?
We've been, well, I guess kind of a little background on that. We've been an OEM for Mastercam on the router side of things for well over 20 years. So that was kind of a natural fit for us when it came to slicing softwares. We didn't find anything existing on the market that seemed to quite fit the way we wanted for what we were doing. So we got with a group of guys to create basically a C-hook with inside of Mastercam. So it kind of all started with our requests and our direction. They are working on a side of that they will have released to industry for other machines. Part of that will be Thermwood specific to what we're doing based off of our needs and accessories on our machine now.
So you were talking about thickness and whatnot. Are the properties pretty consistent given the size that you're actually printing with your process as far as the material strengths and things?
Yes. Yeah, we've done a lot of testing already as far as that goes. There was previous testing done. You know, we're not the first ones to go large scale. We're probably the first ones to go that large of a bead or anything. But we've worked a lot with the material manufacturers themselves to help us dial in and make sure those properties stay consistent going to that large of a bead.
And you have specific materials that you guys typically recommend for this type of process?
We've got a variety that we've used already. I know, just for example, Sabic is working on about a dozen materials right now that are specifically marketed for large-scale additive. Techmer does a huge amount of R&D in this area. They've worked with us a lot. Being able to have both of them kind of by our side, it's easy enough for us to have a customer come to us and tell us what the end results they need. Are they going to be running in an autoclave, at what temperatures, at what pressures? We can take those back and say, hey, what material fits this spec for what we're looking at doing?
One other.
And cost data includes the post-processing machine also, right?
Yes.
And on a related note, do you see this as a production solution or more of a prototype solution? And on that similar vein, what's the thermal consistency concerns over time? We talked earlier about microscopic issues and things like that. Sure, you can post-process and have this thing perfect.
Right.
And then 6 months from now, you're going to make your 5th part, and all of a sudden you notice that the ends are moving or whatnot because it's so big.
Okay. Well, I guess to address the first part, I kind of see it being both. Probably more on the production side than the prototype, to be honest. Just because of the initial cost savings and everything that people are seeing with it. You can get a lot of the same properties you can in traditional tools now with a lot of these polymers and everything. So it's going to take a little bit to catch on as far as the production side. It will probably start more in the prototyping. Just that way people can kind of get a feel for what they're getting from it and the results from everything. But I see that it becoming a rapid change into the production side of things. The second part of that, a lot of that was kind of addressed earlier. As far as the additional machining, coming back and doing filling in certain areas and remachining if need be. It's also something, with the part, we've looked at some ways in creating some of the tools and some of the ways that there would be removable sections that could be problematic. That way you could just reprint new, add those back into the system and be off and going.
All right. Any other questions? Thanks, Brent.
Thank you.
Appreciate it.